The AMDK6 processor uses a version of this technology we call CS44E, a quarter-micron technology using CMOS devices for power reduction. We use both N and P channel devices in the silicon structure that we build to enable circuit designers to build the low-power circuits required to get a multi-million transistor processor at power dissipation levels that can be handled in a desktop device. Quarter-micron patterning is a modern miracle in itself. It starts with a computer-aided design workstation where the designer creates his design information that reflects what he wants to build. That design information is translated into a form suitable to drive a pattern generator, which creates a chrome-on-glass image of the pattern that we eventually want on the wafer. It's written at about 4 times ultimate size so that it's easier to make a highly precise and defect-free master. That glass mask is then used in a photo stepper, where it is reduced down through a highly precise 4x reduction lens to project the image onto the wafer. The mask and the patterning require precision measured in nanometers and a freedom from defects that is almost impossible to conceive. The photo stepper, in turn, uses a 248 nanometer excimer laser light source to get a wavelength of light short enough to form quarter-micron images on the wafer. Because this can only expose a small field on the wafer, we then step and repeat this pattern many times over the surface of a 200 millimeter wafer to fill the entire wafer out with the patterns that we want. Once the patterns are formed on the photosensitive surface on the wafer, we then use etching technology to translate that image into the underlying films, whether it's metal, oxide, or silicon. A variety of plasma reactors with relatively sophisticated plasma chemistry are used to remove material from the unwanted regions. The plasma reactors are used because the gas reactions that occur in this plasma form give us an anisotropic etch, free of the undercut that was associated with the older wet etching techniques of yesteryear. You'll notice that we called our technology CS44E, and the E stands for enhanced. We actually build a 200 nanometer transistor using sub-minimum lithography to build the device for this structure. We chose that to get a little extra boost of performance for the technology. With a 200 nanometer transistor, you have to pay extreme levels of attention to the doping profile in the source and drain region to get adequate electrical performance of the device. In fact, if you measure the out diffusion under the gate region, you find the actual conducting channel, which we call L effective, is actually somewhat less than 160 nanometers. So this is really an extremely small and high performance transistor. Optimizing the performance of this device means you want to get maximum drive current in the on state, minimum current in the off state, and that entails running this transistor at about 2 volts operating condition. That in turn means you need a very thin gate dielectric to get adequate electric field at the silicon surface to get fast turn-ons. We use a gate dielectric of about 4 nanometers or 40 angstroms. It's really only a few layers of atoms. And that means that we have to pay extreme attention to all the factors that affect reliability because we want this device to withstand billions of voltage stress cycles without failure. We also need the gate to be a low resistance path for conducting electricity. And so instead of using just polysilicon, as early devices did, we use a titanium silicide for the actual gate structure to get a low resistance path. You have to remember that a K6 has close to 10 million transistors on it. Each of these have to be built accurately, and each of them have to withstand the electrical cycling that's required. And furthermore, they have to be isolated from one another. Isolation we accomplish by actually cutting a shallow trench in the silicon, filling that with oxide, and then mechanically polishing that back to a planar level to build thick oxide regions between transistors for isolation without taking up an excessive amount of lateral space. In actuality, it takes lots of different levels of wiring to make use of the dense array of transistors you can build. For our K6 device, we have 5 levels of aluminum copper wiring hooking up all the transistors on this circuit. And we actually provide an additional partial level called local interconnect, which is built out of tungsten, to provide a very efficient connection for short runs. So in effect, you could call this 5.5 levels of wiring. The dense wiring patterns have to be planarized to minimize the potential for shorts or opens in building the wiring layers. Having developed that planarization technique, which is used to polish back the oxide and to polish down the tungsten used for interconnect vias, you come up with a method that in fact can be extended to as many levels of wiring as you would like. It gets more expensive, of course, to add more levels of wiring, but we have a modularity here that can be extended on for future generations. Finally, to connect the device into a package, we use a technique called C4, Controlled Collapse Chip Connection Method, in which we construct an array of little solder balls across the chip to provide many dense connection points to the silicon substrate, from the silicon substrate to the package. Well, in fact, we'll need to have a fair amount of evolution of today's technology to get to 100 million transistor capability. Each generation introduces some changes in the technology, and over several generations, the changes can be quite substantial. By the time we get to 100 million transistor devices, and sometime in the first half of the 21st century, I'd expect to see changes in 3 major areas. The interconnect system, for one, will have to see substantial changes in materials. The aluminum copper and silicon dioxide we use today for the metal and the insulator will have to be changed to lower resistance and lower dielectric constant materials to enable us to continue to improve performance as we make faster and denser devices. In the lithography area, we need to continue to reduce the wavelength of light that we use to expose the patterns onto the wafer. Today we're using 248 nanometers. We'll move to below 200 nanometers, and eventually we'll use something called EUV, extreme ultraviolet, with a wavelength about 1/20th of what we're using today. In fact, we've just invested in a consortium to help develop that technology for availability in the next century. Transistors may also need to take a different form as we run into limits associated with scaling the conventional structure we've used for a number of years. We're investing today in all of these areas so that we make sure that they're available for our use as they become required in each new generation of the technology.